Hi everybody, so today we're going to look at some gas equations along with stoichiometry because they go hand in hand. We're going to specifically focus on 2019 question 10c. I recommend that you pay particular attention to this one because this is actually one of the tougher stoichiometry questions I've seen in a long time. So let's have a look. Starting off there, we're asked what mass of C3N4 is produced. Okay, over here. So that's our C3N4. So we look, I just go straight to the formula. Okay, a lot of this now question is knowing the formulas off by heart. The mass equals the number of moles times the MR. And if we do that outright, we'll get of your C3N4 there. The MR you're going to get is 92. Okay, the number of moles we don't know just yet. So we have to use our ratio formula for that, okay, which is pretty standard at this stage. So let's go back up. We have to find out our number of moles of something else, and we're given a number of grams here of the mercury thiocyanate. So if I go over here and I write down my formula for number of moles is mass over MR, and we're told it's 3.17 grams. Now we have to figure out the thiocyanate, the MR of that. Now, when you're getting the molecular masses of this, the S, carbon, sulfur, carbon, and nitrogen there, you add those three up, and then you multiply it by 2, because there's small 2 outside there next to the brackets on the right. Okay, so you multiply it by 2, and then you add in your mercury. Okay, the big numbers, the big 2s, 3s, 4s, whatever, okay, they have no part in figuring out the number of moles initially, not for this equation anyhow. And if you add those all up correctly, you're going to get 317. So the number of moles will equal to 0.01. And that's your mercury thiocyanate. Now, if we look at your ratio, we have 2:1. This is where the big numbers come into play here for the ratios, and only for the ratios. So we have 2:1 here. So that means we have twice as much number of moles here than we do over here, the C3N4. So all I'm going to do there now is go over here, 0.01, divide that by 2, and I'll get 0.005 moles of your C3N4. And 4 there, okay? And that is the value I'm going to use over here. So now we rewrite that. It becomes 0.005 times 92, and my mass, if we do that out correctly, should equal to 0.46 grams. We just highlight that there. Okay, so we had the first one done, and the first one really wasn't the hard one. It's the remainder of them that are a little bit trickier. So I'm going to write down part II now, which is next. And let's read the question. How many litres of oxygen gas measured at STP are required for complete combustion of CS2? Okay, well, if that's the case, we write down our formula straight away. Again, this whole entire question here is about knowing these formulas. So volume equals the number of moles, and that's the number of moles of oxygen, so that's O2. And we're going to multiply that by STP in litres, so that was 22.4 litres. Okay, so we have to figure out what the number of moles of oxygen is being produced there. So let's go back up here and read the question again. How many litres of oxygen gas mixture is STP are required for complete combustion of CS2? Okay, we go over here to CS2. We check it was CS2 over here. It's still 1:1, so that's fine. And we're told in it that there are 3 molecules of oxygen gas. Okay, so we apply the formula again, okay, in terms of the ratio. We know for 1, it's 0.05. So therefore, by that logic there, 3 of them would just be 0.005 multiplied by 3. Okay, and if you do that out, you're going to get 0.015 moles of O2. And we're going to use that then over here. So volume now equals 0.005 0.015 times 22.4. So our volume, and if we do that out correctly, you should be getting 0.336 litres. I want to highlight that. So you just had to know the formula for that one there. So we have that one done now. So essentially we have part I and we have part II complete. Now the next one. What is the number of mercury atoms produced? Now, again, we're going to go to our formulas here again. So mercury atoms. So it doesn't really matter what type of atoms. The number of atoms equals the number of moles multiplied by Avogadro's number. Okay, and we already know Avogadro's number to be 6 times 10 to the power 23. So what's the story with the number of moles? Now, let's go back up to the question. What is the number of mercury atoms produced? Okay, so we need to figure out the number of moles there. Now, we have it here. So these are your mercury atoms here. So that's Hg. Now, if we go back to our, what is the one formula over here? We would be thinking then that we would have 0. I'm going to just write it down as a side over here. Hg, okay, is 0.005 moles. Okay, now we have to be careful here, okay, because if you look at the original question here, these are only half equations really, just to balance them out. If we look at the original question there, we're not dealing with just one molecule of mercury and sulfur together, okay, HGS. We're actually dealing with 2. So what you had to do there is you had to just multiply the number. So if we're dealing with 0.1 here, we're actually dealing with 2, I should say. So there should really be a 2 in front of the HGS. Okay, so therefore we're dealing with 2 mercury atoms. Okay, so therefore instead of having 0.005 moles, we actually have, because that's 2, okay, we actually have 0.01 moles of Hg. And that's the answer we're going to plug in up here. So it now becomes your number of atoms equals 0.01 times 6 times 10 to the power 23. And again, I can't stress this enough, put them all into brackets. Okay, you're less likely to make a mistake. And you'll get 6 times 10 to the power 21 atoms. Now that was tricky, because a lot of students wouldn't have gone back up to the original equation to see how many molecules they were dealing with initially. Okay, so they're actually dealing with 2 mercury sulfide molecules there. Okay, not 1 as we can see here. So therefore we have twice as many mercury atoms over here. Okay, so look, we have part 3 done now. And let's look at part 4, so that's IV. And I'll just split this up again. So IV, now this was a bit tricky as well. What is the total number of moles of gas formed? Okay, so if we're looking at it, the gases are the following ones here. The small g's represent the number of gases. Okay, or represent gases, I should say. Okay, mercury up there is an L, so it's a liquid, so it's no good. Okay, what's the total number of moles of gas? So we have to figure out the number of moles of gas formed for each of these. Okay, so I'm actually going to do this equation up here. It might make things a little bit easier. So for the first one, for SO2, first off, we check our ratios there. Okay, it's HGS, we're dealing with 1 here, and over here we're dealing with 2. So you have to bear that in mind, that there should actually be twice as many down here. So there should be a 2 down here, really. As we said before for the mercury. So everything gets doubled. Okay, including, and I will put it in bold now, the sulfur dioxide over here. Okay, so for SO2, I'll do the first one there. In terms of the ratio there, it should actually be 0.01. Okay, moles. For the first one. Okay, because it's like we have over here 2:2, 0.01, 0.01. Let's come over here to the carbon dioxide. So CS2, if we're looking at it, is 1:1. Okay, so we can actually, this is normal for carbon dioxide. So CO2 there is going to be your 0.05 moles. And there was one next to it, I think it was sulfur dioxide again, wasn't it? Yeah, so there's some more sulfur dioxide, so that's your SO2. So there's two of those, there's two of those. So there's two sulfur dioxides there. Okay, so we're going back to our, what's what I'm looking for there, 0.01 moles. Okay, so we have the first two lines done now. Let's look at the next one. So we have a gas here and a gas here, and we're dealing with C3N4. But look at the ratio again. We're now going from 1 to 2. So we should actually be halving this value here for all of them. Okay, so instead of having a 3 over here, I'm going to rub that out there now, we should have a 1.5. And instead of having a 1 over here, we should have a 0.5. Okay, or a half up there. Okay, so what I'm going to do now is I'm just going to multiply them out. So for our CN2, come down over here, and we're dealing with 1.5 over here, so that's 1.5. Well, if we know 0.005 is for 1, you just multiply that by 1.5, and you're going to get your 0.0075 moles. Go back up here, we're also dealing with N2, and it's half of N2, so that's N2 over here, and it's 0.5 of it. So all I do there is I get my 0.005, I divide that by 2, and then obviously you will get your 0.0025 moles. And now you can add up all of those. So I'm going to do it there now. 0.01, just to be sure, plus 0.005 plus 0.01 plus 0.0075 plus 0.0025, and your answer there is 0.035 moles of gas produced. And that's our final answer there. And again, like, that was tricky. Okay, it was tricky because you had to be cute and realize there that the values here, there should have been a 2 in front of it, for the HGS over here. CS2 is fine, and for this there was actually twice as much as there should have been. Okay, so we had to half everything. Okay, so if I half the last one there, that would have been a 1 instead. Okay, and that was the hardest part, really. Okay, so not a whole pile of students got that one right. So look, I hope that's helped, guys, and best of luck with it. Okay.